welcome to the first combined and gaming center seminar. And our speaker today is Stilck França from Lyon. And yeah, done his PhD with Michael Wolf, and after that was a postdoc in Copenhagen. Now he's in Lyon. And I recently read in the comment section of Scott Allison's blog that Scott Allison will now have a look at your paper. Do you know this?
No, I didn't.
So Raoul pointed this out, and Scott Allison said it's very interesting. I will have a look at it.
Wow, I'm honored.
So now it's officially a stamp of approval.
Thanks.
So,
and as you've noticed, my academic path is exactly the same as Alexander's. So, you know, get used to me, because it's only natural that I'll also come to Oslo now, right? No, just so yeah, thanks for the kind invitation. It's been very nice to be here this week. So I'm going to talk about mostly two papers. Well, the one with Raul Garcia Patron, Alexander just mentioned, and another one more recent with Giacomo De Palma, Candice Jose, and Milad Margian. I'll mention the difference between the two in a few minutes, but let me first try to motivate the problem we're going to look at. So we're going to give some we're going to be given some Hamiltonian on n qubits, and we're going to suppose that the ground state of this Hamiltonian encodes the solution to a problem we care about. In this talk, it will mostly be a combinatorial optimization problem. But let me do some translating here so that we're all on the same page. And please let me know if I'm using some jargon you're not familiar with, okay? So we'll mostly be considering like some observable of the following form. So you have these HIs, and then you have a weighted sum of Zi, Zj operators. But what do I mean by that? These are just Pauli Z acting on qubit I and J, okay? And these weights are between -1 and 1. And you also have some weights on Pauli, just of single Pauli operators, okay? And we want, what is the goal, right? The goal is to find an approximate ground state on a noisy quantum machine. This is the setting we're gonna talk about. What is the ground state? Well, it's just a fancy word for the eigenvector corresponding to the smallest eigenvalue of HI. And in this case, we're also quite happy if we find some eigenvector whose overlap with HI is small. So we might also be okay not finding the optimal solution on the nose, but something close enough in most applications is sufficient. Okay, and these Zi's are just like, I use quantum information notation. I guess most people are familiar with it, just 0 -1. The matrix diagonal. Okay, why should you care about this problem? So this is an NP-complete problem. So you know, you can formulate essentially all difficult optimization problems into this setting I've just mentioned. It's also practically relevant, so people care a lot about solving this and variations of it. So for instance, now we have machines whose sole purpose is to solve such problems, also quantum machines. If you think it's a good idea to solve these with quantum devices, you can even invest your money in that. Since a week ago, D-Wave, which is a company that produces quantum annealing machines to solve such problems, is now available on the stock market. So, you know, people care about finding this thing, and it has a lot of mathematical structure. There are thousands of papers dedicated to finding good solutions to this problem. And the hope now is that maybe we can also use quantum devices to find better solutions. Okay. But some important things should be always kept in mind when trying to talk about you know, potential quantum speedups for such problems. As I said, these are very important, very fundamental. So of course, tons of research has been dedicated to solving such problems. And they're both heuristic algorithms that perform reasonably well in practice. So this means that, of course, you cannot find the best solution, but many times you might find some reasonably good. It's not like we're completely in the dark with classical computers to solve this problem. And And there are even some provable efficient algorithms that obtain like solutions that are within some constant factor of the optimal. So a famous development in this direction is the Williamson algorithm, which is in some way the best you can do classically to solve this. So both heuristic algorithms and provably efficient algorithms have reasonably good performances for this. And of course, also this Hamiltonian, I wrote down this observable, although it is exponentially large in n, because it's like an n-qubit object, this is just a large diagonal matrix, right? Everybody involved in there is just diagonal. So the ground state is just also just a bit strange, just a computational basis state, right? And I should stress this. Again, we might be happy if we not necessarily find the best solution, but a reasonably good solution. So that's also important to mention. Okay, and the guiding question of this talk is, how can we actually compare what we expect to be the performance of quantum computers for solving these sorts of problems against classical machines? Because again, there's a lot of effort, people are building machines and so on to solve this sort of stuff. So any questions so far on somehow the little high level question we want to answer? Well, if not, then let me give you an example. And before I get into the math, I should try to motivate why you should care about this. So there is this, and why it's strategically important. So there's this algorithm proposed by Farhi et al. In 2014 called the QAOA, Quantum Approximate Optimization Algorithm. And it's a heuristic to solve the problems I mentioned before. I looked at how many citations the paper has every year on Google Scholar. You can clearly see an exponential growth. The R squared is quite decent. There, of course, the last point is an outlier. It should grow a lot again, I suppose. So the only logical conclusion is that everybody in this room, and I guess in a few years, everybody in Norway will be working on this. So pay attention. It's the future. Okay. No, just kidding. But these things have gathered a lot of interest. That's the point I wanted to make. And to be honest, I'm a bit skeptical about whether, for instance, in the presence of noise, these algorithms can have a good performance. So how does this QAOA thing works? So essentially, it has some sort of machine learning inspired setup. What you do is you prepare the following quantum circuits. You have some sort of variational parameters, which are these gamma and these zetas. And they are either like unitaries, which are generated by this cost function you want to minimize, or just this H0, which is just the sum of poly x. Okay, and the intuition somehow is that if you act with the poly x, then you are somehow expanding the space you're looking at, and the HI you're zooming in to the ones you care about. But maybe if you're familiar with quantum annealing, this is just a discretization of quantum annealing. And it is known that if you let the number of layers go to infinity, there is a set of parameters, L, that will find the optimal solution when you measure at the end. So in some way, you have to promise that, if you pick this guy deep enough and you choose the parameter as well, you're going to find the optimal solution. But the big question is how big this has to be, because again, this is just a classical thing, right? You just need to go through all the basis vectors and you're going to find the optimal solution. So clearly, there's also a classical algorithm that finds it if you give it enough time. But the hope somehow is that even for moderate values of L, you're going to already do quite well. Okay, so this is, for instance, one example algorithm we're going to analyze today. But we're also going to look at what is going to happen in the near term, because these algorithms, they were proposed as some way of exploring the potential of near-term devices to find solutions. So maybe not when we have like huge quantum computers that can do error correction, but something for the next few years. And in particular, in the next few years, people don't think we're going to have a lot of error correction. So this means that they want to run these algorithms on quantum devices that have noise, that have non-negligible noise in them. And so we're not going to implement exactly what I discussed before, but rather some noisy version thereof. So it is then natural to ask, how will this noise affect this performance? Can we even expect to find good answers if there is some noise in the system? So instead of implementing the circuit we were seeing before, what's actually going to happen is that after, for instance, one simple way of modeling the noise is that after every unitary you implement, there will be some quantum channel T that models the noise affecting the device. And here I'm just going to assume for simplicity that it's always the same. You know, it's a time model, but it doesn't matter too much if you also make the noise depend on the unitary and so on. So this is the more, let's say, a step closer to reality, where we also take into account that the device is being affected by noise because we're not going to have the resources to do error correction. Oh, this is going to come in a second. So at this point, no, but yeah, effectively later, yes. So yeah, and this is exactly the next point I'm going to make. So I'm going to make another strong assumption to get a simple model to analyze this. So I'm going to assume that you have local noise on each qubit. So this means that this quantum channel T I wrote before is just like this, what I call is called the depolarizing noise, which just means that with probability 1 minus p, you're going to replace that qubit by something completely random. Okay. And we can extend this to other noise models, but things get a bit more complicated. I think you don't gain much insight, at least by making the full general statement, but I can, of course, tell you more about other noise models if you're interested. But let's stick to this toy model now. And now what we could do is to look at the expectation values of outputs of noisy circuits under these assumptions, which is what I did with Garcia-Patron. And later and this is gonna be more of the focus today, we're also gonna talk about the concentration inequalities for the outputs. I'm gonna explain what I mean by these in a few seconds. But let's before discuss the intuition of what's going on, okay? So as the number of layers increases, the number of times we apply that noise also increases. So after a while, we just expect that the state we have is just something completely random, just like some maximally mixed state, or at least it will converge to that. And you know, like if you measure a maximally mixed state, you just get a uniformly random input. And this is, of course, not particularly useful or not something we can do we can easily also do that with the classical device. So in some sense, at some depth, this device should become useless. That's somehow clear. But the big question is, of course, how fast does that happen? How much noise can we tolerate before we get to something completely trivial? But in particular, we could ask ourselves how big the step has to be so that we lose advantage against like heuristic classical algorithms, how large the step has to be before we lose the advantage against provably efficient algorithms. But most importantly, we want to decouple this from the ability to actually simulate this noisy quantum circuit. Because simulating noisy quantum circuits is something really hard, but this doesn't mean that they are doing something useful, right? These are two different things. So it doesn't mean, just because we can't simulate whatever a machine is doing, doesn't mean it's doing something useful, right? So we want to be able to say whether we can do something useful with these machines or not, bypassing the question as to whether we can actually simulate them. So let's give let me be a bit more precise when saying what I mean when we say we want to lose quantum advantage or that a quantum device becomes useless. So this will be a first attempt. So we could define EC, which is just the expected value we get with a classical algorithm of our choice. Doesn't matter what we do, you just write some code and you look at the class of problems you care about, and then you see like, oh, okay, this is more or less what I get using this classical algorithm. And then you could also look at the energy you get or the values you obtain by looking at outputs of a noisy quantum algorithm. And then you could say that the quantum computer is not good if the expectation value of the classical thing you're running is smaller than that of the quantum machine, because again, we want to minimize the function. That's maybe one way of saying that the quantum advantage is lost, because again, we want to just minimize this function, and the classical algorithm is an expectation giving you better results. And with Garcia-Patron, we look at this and we show somehow that you expect to lose advantage at depths that are somehow just some constant. This constant in some simulations we did was like 0.1 times the error rate to the -2. So in particular, it does not depend on the depth of the circuit or the particular circuit you're implementing, and it just really depends on the noise rate. So for instance, if you expect 1 in every 100 gates to fail, then you probably already lose advantage at depth 5 or 10. This is more or less what we can show. And with in previous works, they couldn't get something that is independent of system size, and the constants are also significantly worse.
Quick question.
Yes.
You say you lose advantage at step 5. Does that mean you have advantage in order?
Oh, no, that's an
I'm
excellent
sure
point.
not, but,
An excellent point. Yeah. So in this other, I didn't want to talk about this, but in this, but it's an excellent point actually. Or didn't want to talk about this. I forgot to include in the slides. Some other works, including ours with De Palma, Jose, and Marvian, we show that there exist models such that for you to be able to beat classical algorithms, you need to go to depth log n. So in some sense, you can prove that at least for those models, but I mean, they are not all of them. It's just like a rather contrived, if I am honest, subsets of instances for which you need log n depth. So at least for those, if you combine these two results, you see that you'll never get advantage. Yeah, but in general, you cannot say. And you also have to restrict to this QAOA algorithm, because in principle, you could always find the solution in depth 1, because again, it's just a classical bit string. So in principle, you could just like flip the right bits in depth 1 if you lose to it. Yeah, exactly. Yeah. So, in general, you cannot say much, but if you restrict, for instance, to this QAOA algorithm I mentioned before, or quantum annealing or other algorithms, then for some contrived instances, you can show log n lower bounds. Other questions? You had one, right, Tyson? All without error correction. Noise, unitary noise in this setting, in this very simple setting. All I'm going to talk about. So I don't want. So what we do is somehow we find a way of lower bounding the expected value of the quantum device, which is essentially requires you to control the convergence in relative entropy. I'm going to skip this a bit, and just to say that what I find nice is that I can now compare things to experiments, and we compared the performance of what our bound predicts to some experiments done by Google implementing this algorithm. So the black dots are what our bound predicts is the best they can do given their noise levels, and the yellow dots are what they actually observe. So we can clearly see somehow that, especially in the, so to the right, the depth they implement depends on the number of qubits. So as you go to the right, you see deeper circuits, so more noise, and we see that somehow the what our bound predicts is not too far from what they're observing, right? So somehow I find it's nice that we can actually compare this to actual experiments, and is not too far from what we see.
Their performance getting worse with more qubits.
Yes. No, again, the point is as you increase the number of qubits, they also have to implement deeper circuits, so the effects of noise will become more pronounced. Yeah. So 0 is just what you get by random guessing, by the way. So you see that it's approaching random guessing. Yeah.
So one more question. You have the classical efficient, the gray line.
Yeah.
The noise is quantum.
Yes.
Does it mean I would expect that why this straight lines?
Oh, great question. So yeah, so this is for the SK model. So which is just a random Ising model. And for that, there are we know what is the expected value of the outcome. I think it's this Parisi formula stuff. I think Nobel Prize in Physics this year, I think. Anyways, doesn't matter. The point is that we know what is the expected optimal value for these random models. We know a classically efficient algorithm that achieves a constant factor approximation of the optimum, which is this gray line. And they also computed what would be the expected value of the QAOA circuit they implemented if there wasn't any noise. And this is also a constant dependent of the number of qubits. I mean, no, I mean, they do a fixed number of this QAOA thing I mentioned before.
Because if you increase that,
yes,
close to 1 to 1.
Exactly, that is true. And I mean, like for the particular circuit they implemented, they expect if you didn't have any noise, you would see the green line. So even if you didn't have any noise, you wouldn't go above efficient classical. But of course, you could increase the depth and go above. Okay, now we were criticized by our approach, and that's why I don't want to get too much into it, because you know, you could say that the expected value is not what you care about. What you care about is getting a good string. So it could be that with probability 1/2, you get the worst string possible, and with probability 1/2, you get the best. The expected value is 0. This would be an amazing algorithm, right? But according to our previous metric, this would be horrible. So I think this was fair criticism. Of course, I don't expect to see this behavior in practice, but well, if you want to prove no-go results, you have to take into account these things. So a more natural definition of when you lose advantage is to look at concentration inequalities. So we will say that we lost quantum advantage if the probability that the string the quantum computer outputs has a smaller energy than the classical device is exponentially small in the number of qubits. Because then you can at least say, well, I need to sample an exponential number of times to actually see something interesting. So this will be now our definition of when we lost quantum advantage. And later, I'm also going to analyze the effects of error mitigation techniques, which are somehow techniques that try to filter out the noise without doing actual error correction, but more about that in a minute. And for that, we're going to take an optimal transport approach. So I think quantum optimal transport is some sort of a new field emerging that I find quite interesting. There are many cool mathematical questions that are still open. But here I just want to mention what is the so-called Lipshitz constant of an observable. This has been introduced by De Palma in 2021. It's the following thing. So by the way, there are other notions of Lipshitz constant in the literature. But let me I like this one because it's quite simple to write down. The other ones are kind of nasty. And this recovers the notion of the Lipshitz constant of a function, like a Boolean function on the hypercube. And if you pick the metric, it should be the Hamming distance. Okay, so if you just pick age, should be a diagonal operator, that's exactly what you get. And what is the idea? You take an observable age and you look at states such that if you throw out one of the qubits, they are the same. So in some sense, they are the same up to some local perturbation. And then you ask, how does the expectation value of age, by how much can the expectation value of age differ on such states? So in some way, this quantifies how sensitive this observable is to local perturbation. So that's why it gives you some sort of Lipshitz quantity. So yeah, and why do I, one particular thing I like about this is that one can show Gaussian concentration inequalities with this. So with this sort of framework, one can define like Wasserstein distances and things like that, and then also use machinery that is similar to what people do in classical probability theory to define concentration inequalities. So, for instance, you can show the following inequality. So here I'm looking at the following quantity. We take some age, some observable age, and we measure it in the eigenbasis of age. So we measure the maximally mixed state in the eigenbasis of age, and we're now asking what is the probability that that outcome deviates by epsilon n of the mean. And I assume this age should be traceless, so the mean is 0. And you can show something like that, which is, quite exact. It's more or less the same you would get with like Levy's lemma or something like that, right? For classical stuff. And now we're also working on extending such inequalities for weakly correlated states, product states, and so on. Trying to recover similar results in the classical literature. Okay, so this will be our departing point. Concentration inequalities like that. So, and just one quick comment. For most classical algorithms, you can again get some solution. Sorry, for most problems, you can get some solution which is a constant factor away from the optimal one. And the optimal usually scales like n times the Lipshitz constant of the observable. So it makes sense to sort of put the Lipshitz constant in the normalization there. Inside the probability, so that then the right hand side just becomes independent of age. Good. Now again. Oh, sorry. Oh my God, what a mess. Let's see. Okay, no. Any questions? I see, sorry. Okay. So what is the intuition again? Our noise is driving the system to the maximally mixed state. So I just showed you like how like the measurements on the maximally mixed state concentrate. So the question is, if we're going to that state, we would expect somehow that we at some point will observe a similar concentration profile for the output of the quantum device in the maximally mixed state. But of course, once again, the question is, when does it happen, and how do we show that like the concentrations will be similar? And for that, to show this, we'll work with the so-called sandwiched Renyi divergence, which was proposed independently by Wilde and others and Thomas Michel in 2013. And for two full-rank states, this is just given by that thing. And it's a very nice quantity. For the operator algebraists in the audience, this is closely related to the LP norms, non-commutative LP norms. introduced by Pizier, and I think I forgot the second guy, Shu, I think. They have found multiple applications in quantum information theory, for instance, showing strong converses through the capacities of quantum channels. And why do we want to use them? Well, we show that the following thing holds. So if you take any observable between 0 and the identity, and you look at a state rho, then you can bound the trace E rho by a quantity that depends on the probability or like the overlap of E and sigma plus something that is proportional to the sandwich Renyi divergence between rho and sigma. And these Renyi divergences, they are somehow some sort of distance measure. So this lemma here, it sort of tells us that these quantities allow us to transfer concentration properties, right? Because if you see d alpha as some sort of distance measure, you're seeing that you can also easily, if that thing goes to 0, then probabilities will also be more or less the same for the two states, right? No, you don't. You don't. No. I call it this. Well, I mean, it's 0 if and only if rho equals to sigma, but it's a divergence. It's not a metric. So you don't have a triangle inequality unless you let alpha go to infinity. But for instance, you have what is called data processing, which is something that means that if you apply noise to both rho and sigma, this thing can only contract, and so on. So it has some very nice properties, but it does not satisfy the triangle. And it's also not symmetric. So if you exchange sigma and rho, it's not the same. Other questions? And proving this is, so this is what I just said, and proving this is quite simple. You just use some standard trace inequalities and play around with it. Nothing too complicated. Oh, and the Hölder for like matrices, you know, like you can define the Schatten P norm and that Hölder, yeah. Oh, no. So exactly, no. I think it's so it's like you first step is you do Hölder, and the second step is you do yeah. So let us now combine this with this Gaussian concentration bound I mentioned before. So we see that if we pick P epsilon n to be the projector onto the subspace, right, where the outcomes of the string are larger than epsilon times the Lipshitz norm times n, right? If you plug this concentration bound we have over there into the formula there, then we see that we have this minus epsilon squared n over 4 popping up, right? So what does this tell us? This tells us that as long as this sandwiched Renyi divergence is smaller than epsilon squared over a times n, then this minus epsilon squared n over 4 term will dominate, and you'll get some sort of exponential decay in n. So we see that the only condition we need to transfer this sort of concentration profile is this condition that the relative entropy is smaller than some constant times the number of qubits. Okay. Good. Oh, and again, this can then be used to get show that there will be no exponential quantum advantage, because if we pick epsilon to be like whatever we get with the classical algorithm, then we'll know that the probability that we sample something which is outside of what we can do with a classical algorithm is exponentially small. So with this, we can now say by how close we have to get to the maximum mixed state, at least in this Renyi divergence. Yes.
Quick question. I think you already said it, but you don't mean exponential speeder, right? Because there was never any exponential speeder for these type of settings with maximum. I think it's only expected to be at most polynomial.
Yeah. So you know, like there. Well, I guess in some cases you can. I mean, some contrived cases you can get more than polynomial advantage. But I guess the point here is that, you know, if that condition is satisfied, then you're just gonna look at like really trivial things somehow. That there will be nothing like even remotely interesting going on. Does that make sense?
I guess.
Yeah.
Thanks.
Yeah. Okay. So how do we get that condition of this Renyi entropy becoming small? Well, we do the following two observations. Again, this phi L is the circuit after you have L applications of the noise. So what we use is our so-called contraction coefficients and the unitary invariance of this divergence. So what is a contraction coefficient or a strong data processing inequality? So this is one of my favorite topics. So as I mentioned before, we know that if you apply a quantum channel to both arguments of this divergence, then it can only contract. It will never increase. And here I'm assuming further that this quantum channel will preserve some state sigma. So it's a fixed point of the map. So if we take Q equals 1, this is just a statement that holds generally that if you apply a channel, this quantity will never increase. But for most channels, it will actually decrease strictly. And that's what we want to capture. So this is what this parameter Q is capturing, that if you apply this quantum channel, this divergence will always decrease by a factor Q. And if we are in this sort of setting, what's going to happen is that every time we apply one of these T's, no matter what this input state is, because important point that we have to mention is that this constant Q is independent of the input, we're going to get closer by something that depends only on Q. The divergences, they are also unitarily invariant, which means that applying these unitaries won't change the distance to the maximally mixed state because it's also unitarily invariant. So every time we apply one of those T's, we get closer by a factor of Q. Every time we apply one of those U's, the distance won't change. So we get some sort of exponential decay. So again, because of the unitary invariance, if we pick sigma to be just the maximally mixed state, then this distance won't change whenever we apply unitaries. And we can repeat this argument, and we conclude that if we have L uses of the channel, if we apply the noise L times, and it contracts by Q, the unitaries again have no effect, and every application will decrease it by a factor of Q. So we have a total decrease of Q to the L. And it's a fact one can check that actually, if you look at any state and the maximally mixed state, this divergence is bounded by N. So you get this sort of inequality. So we conclude that all we needed was to show that this thing was smaller or equal than some epsilon squared over 8 times N. And if we have such a result that the channel contracts, then we get this condition after applying the channel enough times. So we see that the only thing we need to now control is this parameter Q. We need to look at how this Q behaves for channels we care about, right? And then we get a result that will have exponential concentration. And now, again, this is one of my favorite questions. How do we control Q? We're going to focus on the case where the channel is just some tensor product and it's unital. And we'll be interested in inequalities which tensorize. What does that mean? This means that this Q is independent of the number of copies of the channel I use. So I know that no matter how many copies of the channel I have, no matter how entangled this input state is or whatever it is, I want this thing to contract by Q. This is that's what we mean by an inequality that tensorizes. And there's some really nice math behind this sort of question. This is like equivalent actually to looking at the hypercontractivity properties of these maps and looking at the multiplicativity of norms. So there's a lot of machinery behind this. I quite like it. But back in the old days, Alex and we got estimates which tensorize for quantum dynamical semigroups. And more recently, we showed how to use those results we had to actually get inequalities that tensorize for essentially any quantum channel of product form and alpha equals 2. And we show that, again, using these old results with Alex, not so old actually, so if you take the second largest singular value of n, and because n is a quantum channel, the largest singular value is always 1, okay? Then you contract by this much. So the second largest singular value to 1.44. It should be 2 actually, but that's the right result. But for any channel, we can only show 1.44. Anyways, so this somehow shows that as long as you have some product channel, then you always have this constant contraction rate. And in particular, we again see that if we have a depth that is proportional to like S2 to the -1 times some constants, or 1 minus that, sorry, then you'll be exponentially unlikely to see any sort of interesting output string. So, you know, the noise really limits everything. Okay, so that concludes somehow the first part. I just want to now discuss maybe some extensions of this sort of result. So any questions at this point?
For P equals 0.1, that would be 9.
Yeah, something like that. Yeah. Yeah.
You know, have you tried anything where you can see changes from the level?
Oh yeah, so that's simple. If you make the assumption at all points that the noise is still like unital, so that it maps identity to identity. If you're okay with making that assumption, then you can do something similar. And then instead of having like this S2 to the power 1.44, you have the product of different things. But the technique works exactly the same. If you're not comfortable making the assumption that the noise is unital, things are more complicated.
Wrong with that 1.1.
Huh?
For 0.1, it's 1 over 1 minus 0.1, right?
Mm-hmm.
And that's 1.111.
Oh.
It was not that one. Step 9 is that 1. Right.
No, because it's there's a typo there. I'm sorry. It's like 1 minus S2 to the power.
Oh, okay.
Yeah,
Okay.
sorry. So there's yeah. So that's why. Yeah. Any other questions?
The realistic assumption that the noise is unital?
Oh yeah, great question. And I've heard many different things. So it's difficult to say, right? So it depends highly on the platform. It depends on the dominating noise source. So for instance, there's also a quantum annealing version of these results. So where you don't consider a circuit model, but an annealing model. And I recently was at a conference on quantum annealing, and they were like, oh no, this noise model is garbage. They were saying that it's completely unrealistic and blah blah blah. So, but on the other hand, if you look at the comparison of what my bound predicts to what the Google people observed, I see a lot of agreement. So at least for quantum circuits, I feel that I'm onto something that is realistic. But for instance, I haven't tested. That will be something I mentioned in the end. I think it will be nice to test this more generally. If this technique, the sort of rule of thumb, the predictions, if they are good for all platforms, or just, for instance, superconducting qubits. I mean, I also just took one experiment right there. I think it would be nicer to compare it to other platforms. Yeah. Maybe a nice project for bachelor's or something. Yeah. So I don't know. Depends a lot. Yeah. Okay. So as I mentioned, some people other criticism we got is that we're not considering the case where you perform some sort of error mitigation on the quantum device, on the circuit. What is quantum error mitigation? I think there is no universal agreed upon definition, but in my understanding is it's something you do after you run the noisy circuit to sort of filter out the noise. And it's important to distinguish two things one could do to filter out the noise. One thing is two versions of what you could mean by filtering out the noise. So one is to actually filter out the noise in such a way that you actually get a bit string from what you would do from the clean circuit. So you filter out the noise in a way that you get a sample from a measurement. The other way you could filter out the noise is to just get like clean expectation values from dirty ones. So you don't get a string which comes from an output, you just get like some statistics. But in our case, we're mostly interested in getting some sort of bit string which corresponds to a solution of the problem we care about. So I would say that for our case, this first version where you get a clean sample is more relevant. But we're going to talk about the two versions. So as far as I know, the only error mitigation technique that gives you also like clean samples is this one by Huggins and Ballins. I think one group calls it virtual distillation, the other calls it virtual cooling. And their idea is roughly that if you assume that you have some noisy output and the clean one is the leading eigenvector of this noisy output, then it's not too difficult to convince yourself that if you take rho to the k then and normalize it, then this state will have significantly more weight on the leading eigenvalue, because all other eigenvalues will decay faster as you take powers of rho. So this is one way of cleaning your state, right? You just look at rho to the k. But going from rho to the k is clearly like from rho. Performing this transformation clearly isn't linear. So what they do is they take k copies of the output state, and then they do some quantum circuit on it. So you need a quantum memory to do this sort of operation. And then with some probability, if you do things right, you get as an output that state, rho to the k or normalized. So in principle, this would be nice, right? Because you could then, by using this and just picking k like logarithmic in the noise strength or something like this, you could get a pretty good approximation of the clean state. But again, you cannot do this deterministically, of course, because it's a nonlinear transformation. And in our paper, we show that the probability of success for such a procedure is exponentially small, not only in the depth, but also in the number of qubits. So like it's very unlikely that such an approach can succeed. But there's also this weaker notion where we are not necessarily interested in obtaining a sample, but maybe just the expectation values of observables with respect to a clean circuit. This is what I call weak error mitigation. And there we have a weaker. There we also show that the number of samples you need to get that has to scale exponentially in the depth. And in particular, all of these bounds I've shown so far had no dependency on the number of qubits. And we close this gap by showing that, and in some sense, this is also tight, because if you do nothing, right, if you just have the noise acting in parallel, then the convergence rate, that shouldn't depend on the number of qubits. It's all doing things in parallel. But the circuits for which this sort of behavior, like a decay that only depends on the depth, are exactly those which are sort of boring, right? The circuits where nothing happens. So what we show is that somehow the picture is much worse if you look at deep enough circuits. In particular, if the depth is logarithmic in n, then this decay rate starts to also be not only exponential in the depth, but in the number of qubits. So in some sense, all errors count. We map to prove this sort of stuff. We map these problems of error mitigation to distinguishability of quantum states, and then we use this machinery to obtain the lower bounds. And once again, the crucial step is to obtain a good control on these sandwiched Renyi divergences between noisy quantum states and between outputs of noisy quantum circuits. Okay, so let me conclude now. As I mentioned before, things are more intricate when we don't have this assumption. We can still state some results, but then, for instance, one nice thing we had here so far is that the results are completely independent of what you're doing. If we drop this assumption, then this is no longer the case. But if we have these QAOA-like circuits I mentioned before, then we can actually still say something, get some analytical results, and so on. But yeah, it requires significantly more work. Exactly, and I think it would also be interesting to show this decay that also not only in the depth but in the number of circuits for more noise models. We can only do this for some, let's say, kind of artificial example. So if you want to get decay in both the number of qubits and the depth. And as I mentioned this already, we can also do all of this in the annealing model. And I think that sort of, if you think that this model where you have like some noise that could maybe be approximated by unital noise, and you just do things naively, no error correction, nothing on top of the circuit, you know, this is not going to work. You need to put in a bit more work to get interesting outputs. I'm at least I would not expect that error mitigation on its own can change the big picture. Maybe it can reduce certain exponential scalings, but like this would correspond to changing an exponent in the scaling of something from, let's say, 2 to 1.7 or something, which can make a big difference, right? But not too scalable. I'm personally of the opinion that if we want to expect good results from such algorithms, at least a bit of error correction might be necessary. And but there are many open problems, right? So one thing that I think is quite important is to drop some of the assumptions we make and get a better understanding as to what exactly are the results, the resources we need to bypass such results. Generalizing to more noise models is something, of course, important. On the mathematical side, I think very many important questions are unanswered about these contraction coefficients I mentioned before. So like hypercontractivity questions and tensorization questions, and these are all very important for this sort of technique. And in particular, I would also maybe go beyond that, because these always give you like worst case estimates, but the contraction typically is much larger than this worst case estimate. And that's also something we already talked about. It would be nice to look at what actually happens on other devices besides this Google experiment I mentioned. And with that, thanks for your attention. Questions?
The iPhone question also. So you mentioned you also extend this non-dimensional noise.
Yes.
So I mentioned that. So do you then quantify the distance to the fixed point, or?
Yeah. So the assumption is, so I need to make some assumptions. As I said, it has to be this QAOA like circuit.
Which you mean unitary modes, or?
Yeah, but also the particular unitaries.
Yes.
And I assume that the noise is driving you to a diagonal state. So it's not maximally mixed state, but it's like classical. Exactly. So again, it cannot be independent of the circuit you're implementing.
Yeah.
It's specifically for like annealing like circuits. So it really uses the structure. And in the result, we actually need your data processed triune inequality. So yeah.
Another question, because now that it's somehow you have to QAOA like circuits. Is VQE other variational approaches? Are they QAOA like in that respect or not?
Okay. Well, no. So yes and no. So the point, what we're really using here is the fact that in the end, you want to solve a classical problem. So somehow when you do the annealing, you start with like let's say some transversizing. So there's some quantumness to it, and you end at the Ising model, which is this diagonal. And we're using the fact that the noise will also make you converge to something diagonal. So somehow the crucial assumption here is that the fixed point of the noise is also like commutes somehow with the Hamiltonian. So
okay,
that's,
so if it's non-Ising type, then it
might be different, exactly. Yeah. So yeah, that's an important point. So in the beginning, I said that like most of the results transfer to also not looking at classical problems but quantum problems. Here, as pointed out, is an important exception. So for extending the resolution noise that is not unital, we really need again that we really use the fact that the problem we're looking at is classical. For quantum problems, I don't know how to do it. Any other questions? Okay.
I have to maybe my question. So is there any conceptual, I mean, the model of noise use is one thing, but it's sort of, I would think that would be more realistic to model the circuit itself. I mean, each unitary process could be slightly wrong. Instead of injecting like the sort of white noise periodically, because that seems to me to be much more dramatic somehow.
So what you're referring to is like having control errors on the unitary, right? So at each step, correct me if I'm not translating what you said, okay? So instead of implementing e to the minus h, where h is something we want to implement, there is some fluctuation there, there's some error there, right? So if that sort of error if that's the sort of error you're talking about, then we also analyze it in the paper. So what we call control errors in the implementation, and then in like a continuous time model, and then we get to similar conclusions. So if you do it in that picture, things don't change much. I presented it in this way because I guess it's the simplest way to present it, at least from my perspective, but you can also do it the way you suggest, that like you have some sort of error when you implement the operation.
Well, my second question is, so with this model of noise, the results seem rather dramatic, right?
Yes.
It's very provocating. So is there any other, I mean, what kind of noise would not give this kind of, is there any other noise model that sort of
So, I mean, let me give you an example of my worst nightmare, in the sense that like my techniques break down completely, which is just like pure amplitude damping, which is quite relevant. So that's why it's bad for me, because if you have pure amplitude damping, so amplitude damping means that, you know, roughly speaking, it's not exactly that, but instead of replacing the state you have by the maximum mix state, you replace it by 0. This sort of noise model is not easy to treat with these techniques. So if I had to guess a physically like reasonable noise model where things could be different, it's something where you have a highly biased noise, like in amplitude damping. So the problem is that in that case, the fixed point of the evolution will no longer have full rank. So most of the things I know how to do don't work. So if I had to venture a guess, it would be a highly biased noise source. That then things maybe then it might be easier to actually filter out the noise. But again, just because these techniques don't work doesn't mean it will be better. But if you want a simple noise model for which this all breaks down, pure amplitude.
I think like one thing that like these techniques where they use like the entropy somehow builds up in the system, right? And we're only by unitaries, you cannot remove the entropy. But this entropy damping of what you're talking about, right? This cools down when it removes entropy. So you could have part of the system that you use to remove the entropy, and if this part of the system is large enough, you can remove all the entropy that builds up in the circuit that you care about. We can somehow do that kind of error correction using unitaries and the noise itself to prepare a pure answer that you can use to implement the error correction. Yeah, I think there may be a reason why this cannot work.
No, it cannot work for any circuit, right? But because what you, yeah. So it's unclear whether, you know, if you're in the same model, say where you just do unitary noise, if you have amplitude damping instead of depolarizing, whether this changes the picture dramatically, I personally don't believe so, but I also cannot prove it. So yeah, I cannot offer more than this.
Okay. Let's think about it again.
Thanks.